This training module is an overview of methods used to simulate pre-storm streamflows as part of the upstream stormwater volumes with the stochastic empirical loading and dilution model. We use the term pre-storm flow rather than base flow because the streamflow at the beginning of a runoff event commonly includes runoff from a previous event. Pre-storm flows are especially important because they provide much of the initial dilution that may occur at the beginning of an upstream runoff event while the highway is discharging to the stream. Pre-storm flows also may contribute a substantial portion of the total storm flows throughout the storm. This is training module 4.01b for the Stochastic Empirical Loading and Dilution Model SELDM. This presentation has 17 slides and will take about 9 minutes. It was prepared by the U.S. Geological Survey in cooperation with the Federal Highway Administration. This training module has 5 learning objectives. At the end of this module, you should be able to describe the relation between pre-storm streamflow statistics and stormflows, pre-storm streamflow variables, the methods used if there are pre-storm flows equal to 0, the methods used to generate non-zero pre-storm flows, and the name and format of the pre-storm streamflow output file. This presentation is a brief overview of the technical details for estimating and using pre-storm streamflows. Please see the Federal Highway Administration Stormflow Report, FHWA-HEP-09-005, and the SELDM Manual, USGS Techniques and Methods Report 4C3 for more details. SELDM uses a simple mass balance approach to calculate flows, concentrations, and loads by storm and by year. It uses Monte Carlo methods to generate precipitation, pre-storm flow, and runoff coefficients to generate the storm flows. Downstream flows, concentrations, and loads are calculated from upstream values and runoff or BMP discharge from the site of interest. The highway site in this diagram may be almost any land use that could be characterized with an impervious fraction and representative water quality statistics. As this schematic diagram indicates, the pre-storm flow times the runoff duration is added to the upstream runoff to calculate the total upstream storm flow used for the loading and dilution calculations. The amount of storm flow depends on the amount of pre-storm flow and upstream runoff that occurs while the highway runoff outfall or the highway runoff BMP outfall is discharging to the stream. In SELDM, the pre-storm flow is held constant for the duration of the runoff event. As this diagram indicates, pre-storm flow statistics are primary variables for calculating upstream storm flows. Monte Carlo methods are used to generate a population of pre-storm flows from the upstream basin. The stochastic precipitation event, runoff coefficients, and hydrograph timing variables also determine the volume of concurrent flows. This schematic diagram shows the flowchart for entering input data and for running a SELDM analysis by using the model's graphical user interface. Streamflow statistics are specified on the second hydrology form in the interface, which is also the 10th form in the progression from the analyst form to the run SELDM form. SELDM supports the environmental decision-making process because it is pre-loaded with the streamflow statistics needed for an analysis. This facilitates rapid development of robust planning-level estimates that can be refined with data and statistics from nearby sites that are available within SELDM. It is also easy to get statistics from almost any stream gauge in the country from StreamStats to use in a SELDM analysis. If you use regional values or nearby sites in SELDM, you can assess conditions at many sites in a day. If you want to do more work to look for similar basins in StreamStats, you can still assess conditions at many sites in a few days. If you need to collect defensible data at a site of interest, however, this will cause substantial delays and cost increases that will be orders of magnitude greater than the initial modeling effort. SELDM uses EPA Level 3 ecoregions to group statistics from 2,783 USGS stream gauges. This map shows the spatial distribution of the selected stream gauges with respect to the ecoregions, which are shown as colored polygons on the map. Ecoregions are areas with similar precipitation, climate, physiography, and geology. These variables commonly are used to predict flows at ungauged sites. The ecoregions do provide some level of discernment, but there may be large variations in statistics within some ecoregions. Users can easily select statistics from among the individual stream gauges pre-loaded into SELDM. This is a screenshot of the SELDM streamflow form. This form provides 5 methods for selecting or entering pre-storm flow statistics. These methods are the ecoregion average, ecoregion median, selected station average, selected station median, and user-defined. The first two options are to use the average or median of statistics for all stations in the specified ecoregion. The second two options are to use the average or median of statistics from one or more stations that are selected to represent conditions at the site of interest. The final selection is user-defined. This option lets you input entirely new values or edit existing values. The user-defined option is designed to facilitate a sensitivity analysis and to allow input of site-specific statistics. This is a map showing the location of 18,122 U.S. Geological Survey stream gauges in the conterminous United States that have SELDM statistics in StreamStats. These gauges have data for at least 3 years during the 1901 through 2015 period. If you go to StreamStats and click on a stream gauge, you can see these statistics. Please see our video on the availability of streamflow statistics for more details. SELDM uses four statistics: the fraction of zero flows and the average, standard deviation, and skew of the logarithms of non-zero flows to model pre-storm streamflow. The other statistics are provided to assess hydrologic similarity among potential stream gauge selections. The statistics within SELDM are expressed in cubic feet per second per square mile, so that statistics from stream gauge locations can be applied to points of interest with various upstream drainage areas. A cubic foot per second is enough to fill an Olympic-sized pool in a day, so we can fill one pool per day per square mile at this rate. The proportion of zero flows in the stream flow records sets the threshold for the proportion of zero pre-storm flows in the simulation. During each SELDM run, a uniform random number between 0 and 1 is generated. If the proportion of zero flows is greater than or equal to this number, then the pre-storm flow for that event is set equal to 0. If not, that uniform random value is rescaled to a uniform random number between 0 and 1 by using the proportion of zero flows. This rescaled number, UR, is used to calculate the pre-storm flow with the frequency factor method. The frequency factor method is used to generate the non-zero pre-storm stream flows by using the mean, standard deviation, and skew of the logarithms of non-zero mean daily flow data. The skew of the logarithms of the stream flow data define the relation between the probability of occurrence and the frequency factor. If the skew is equal to 0, the random variates have a normal distribution, and the stream flows would be log-normally distributed. Non-zero skew values result in variates with a Pearson type 3 distribution, and stream flows with a log Pearson type 3 distribution. Pre-storm flow rates are written to the -ps.txt output file in the analysis directory under the FHWA-SELDM folder on the root drive of the computer. This file contains a list of the stream gauges with site characteristics and statistics for the proportion of zero flows, the geometric mean flow in CFSM, and the geometric standard deviation and skew, which are unitless, in tab-delimited format. The file also contains the plotting position and upstream pre-storm flow rate in cubic feet per second for each event in the simulation. As the file indicates, individual storm events are identified by sequence number and annual load accounting years. SELDM, however, generates each value randomly. There is no serial correlation. The order of the storms does not reflect seasonal patterns. In this module, we learned that pre-storm streamflows may provide substantial amount of total dilution, and the pre-storm flow statistics determine this contribution. The pre-storm streamflow variables are the proportion of zero flows and the mean, standard deviation, and skew of the logarithms of non-zero flows. Conditional probability methods are used to generate some storms with pre-storm flows equal to 0. Non-zero pre-storm flows are generated by using frequency factor methods with the mean, standard deviation, and skew of the logarithms of non-zero flows. The pre-storm flow output file has a -ps.txt suffix and has values in tab-delimited format for use with other programs.